In this video, we'll continue our discussion of spherical coordinates with the problem triple integral over t of yz dv, where t is the solid bound. Okay, this is a sphere. If I could spell sphere. There we go. Sphere. This is a cone. All right, so we're dealing with the intersection of a sphere and a cone. It's opening up, so probably just the top half of the sphere. All right, so to do spherical coordinates, we have two different directions to help us find each one. If I let x equal 0, I get y squared plus z squared equals 4. And in the other one, I'm going to get z equals the square root of y squared. Now be very careful with this. This is z equals the absolute value of y. We don't know what y if it's positive or negative. And when I square it, it makes it positive, meaning I'm always going to get a positive result out, which means I need the absolute value. Now, I don't know, the circle is here already in the xy plane. I drew that. I do that in advance, so I don't have to spend time in the video doing it. So that is the yz, that's the circle. The absolute value function, if you don't remember, is a v. I'm going to try to get that right down the middle as best as I can. There we go. And it goes this way as well. Right, this is y, or z rather, the square root of y. So they want the solid bound between the sphere and the cone. So I imagine that we are talking about here. All right, so let's see if we can get some bounds from that. Okay, rho, phi, and theta. All right, rho, nice and easy to see. It's caught between 0 and 2. Right? Remember, rho is the distance out. So it's 0 and 2. And then phi is from 0, that's the top. And then this angle, it's right in the middle. It's our cone's right down the middle, so it's pi over 4. All right, the last thing we have to do to find z equals 0, or to find theta, we let z equal 0. Okay, z equals 0 is going to give me x squared plus y squared equals 4. This is a circle with radius 2. We can look at that or think about it. It's just a circle. It's the whole circle. So the bounds for my theta are 0 to 2 pi because it goes all the way around. We could draw a circle on the xy plane and see it, but I think we can use our brain to see that. All right, so I have my bounds now. Now we just have to convert our integral. So let me write it down here. Over t of yz dv is equal to, okay, let's try to fit this in, theta 0 to 2 pi. Phi is 0 to pi over 4. And then the last one, rho, is 0. Let's fix that rho. It's gross. Rho is 0 to 2. Right? And then we have y times z. Okay, y was rho sine phi. And then since it's y, it's sine theta. Times z has its own. It was rho cosine phi. Then we have to put our Jacobian in. Rho squared sine phi. And then d rho, d phi, d theta. Looks really complicated. It's just each part. Remember this, if you didn't catch on, this was y. This was z, just using the coordinates from the conversion. The formulas given from coordinates part 1. We can clean this up, so I'm going to do so because it's easy for me to duplicate. Right, okay, I have rho to the 4th. It's counting all of those. I have sine squared phi. I also have sine theta. And I have cosine phi. I guess we should have put those together. I mean, it really doesn't matter, but it feels good to put the phis together. And then sine theta. I think I got everything. Those were taken care of. Rhos were taken care of. Cool. And then I got d rho, d theta, or phi, sorry, and d theta. If you were to work this out, and this one's harder for me to play with the angles and figure something out, we get 0. So whatever this integral is, the integral will get me a 0. If I was looking for something else, I would change maybe my thetas. just to play with it to see what changes as I move around. The Z's may change, the Y's may change. I'm just going to leave it as it is because we would just be playing with it to see what numbers we would get, and that would be important in context. Again, assessment-wise, I'm not going to give you anything that would be subjective in this sense.